Okay, so this week I want to continue on with some more of the work I've been putting off for the dyno for quite a while. So what I want to do this week is I want to do some calibrations on the load cell for the dyno. And the load cell is back in there, and we'll have a look at that in a second. But yeah, this is something I've been putting off for a while. I have done some basic calibrations to get the torque reading, but I want to do it a little bit better than the way I did it before. So what I'll do is I'll show you the way I did it before, and then we can have a look at how I'm going to do it today and why that's going to be considerably better than before. This is just a sketch of the it's an S-type load cell that's in there, and this is the way I calibrated it before. Was I just the top of it was secured to the ceiling, and I just put a weight on it down here, and then that pulled down on the load cell, and I was able to calibrate it that way. When I start the program that starts reading the load in from the load cell, it zeroes itself each time I start that program. Something about the load cell, and I'm not an expert on those things, but this is what I think it does. It's probably got a strain gauge or an assortment of strain gauges inside of it, and probably what it does is it puts out a different voltage depending on how much load is on it. This type of load cell it works in compression and in tension. So the way I did the calibration before up to this point, I hung the load cell from the ceiling, and then I had a weight down here. Anyway, it was just a really simple thing. I just needed to get something going, and all it was it was a 5-gallon bucket with rocks in it and a couple other weights. And then I took that bucket and I weighed it on a bathroom scale, and I found out how much it weighed. Anyway, that's the way the program works. It needed to know it zeroes itself at the beginning of the calibration, and then it prompts you to hang a weight on it or apply a weight to it. And then what it does is, I think what it gets from that is like the slope of this curve here. So you probably start out at 0, and then you're going to end up here somewhere. And then once you know that, you got a point and you got the slope, and then with those two things you can kind of figure out the equation for that line, and then you could take the output of the load cell and convert that into the weight. And then the way I get the torque from that is I take that weight and multiply it by the distance from the center of the absorber to where the load cell is. What I want to do is rather than just use one big weight, I've got a collection of different weights that I've weighed, and I know what they weigh. And what I want to do is I'm going to apply these things in steps. So there's 7 of them all together. Well, there's 7 pieces I'm going to put on all together. And the idea is that, if you only calibrated here down at 0 and here out at the end, you could end up with errors along the way, because basically what I was doing there is I was assuming that the thing was putting out a linear voltage with respect to the amount of weight that was on it. So what I want to do is apply those weights incrementally so that the outputs are reading correctly. And the idea is that if you zeroed it there and then looked at it up here, you could be completely accurate here and here, but there could be places along the way where you could have errors. That's why I'm going to calibrate this way. So let's go inside the test cell and have a look at what I put together to do these calibrations. Okay, so here's that S-type load cell that I was talking about before, and it's from Omega, so it's a fairly decent load cell, and it goes up to about 1,000 pounds of force. It's sized appropriately for what I'm doing here. So the way I've been doing this is I measured the distance from the center of the absorber out to here where the force is being measured. So if I know this force and I know that distance there in feet, I can calculate from that lever arm and that force what the foot-pounds is, or what the torque is. The way I'm going to do the calibrations is I made this bar. What I'm going to be doing is I take this bolt out of here, and then I fix this bar to the other side of here. It's tight quarters in here, it's hard to get the whole thing in shot, but this bar bolts onto here, and what I know is out here on this end, right here, there's a hole drilled. When I bolt this into place, I know that this hole here is very close to 3 feet away from the center of the absorber. So what I'm going to do is I made a carriage that I hang onto here, and there's going to be weights that I apply onto the carriage, and then I've weighed all of these things, and the bar, the carriage, and I bought a scale to weigh the weights with, and they're 20 pounds each, but they, you know, that's what they're advertised as. The actual weights are slightly different than that, so I needed a scale to measure all these things and find out exactly what they weigh. Everything except for this bar here. I wish I could get it all in the same shot, but it's really hard to do in here. So those 2 bolts fasten to here and in that hole there. And then what I did was I marked the center of this bar. The weights that I'm going to be hanging on here to apply torque to this, they're going to be attached through that feature there. All the weights that I'm going to hang from this bar, they're going to be 3 feet from the center of the absorber, so that any weight that I hang out there is going to be whatever it weighs times 3 feet, and that's going to tell me how many foot-pounds of torque is going to be applied through here. So they're all going to be like that. They're all going to be 3 feet away from the center of the absorber, except for, because this bar isn't counterbalanced, I need to account for how much torque the bar weight is applying to the system. So the way I'm doing that is, because this isn't counterweighted, what I did was I weighed this, came out at 7.44 pounds, and then I found the center of the piece. And this is the only piece that's going to be applying a load to the system at less than 3 feet. Because what I needed to do was I found the distance from the center of the absorber to the center of this bar, which is basically the center of gravity, except for, you know, obviously those holes and things moving around a little bit, but I'm not going to get that crazy about it. So basically I found the center of gravity of this, and where that is, I'm going to calculate the torque that this is going to impose on the system by that weight and the distance from the center of the absorber to the center of gravity of this, which came out to be a little less than 2 feet. The next thing we'll do is we'll go back out to the whiteboard, and I'll show you how, if everything goes right, I'll show you what should show up on the screen in terms of foot-pounds as I add the components and the weights to the calibration setup. So I'm going to have 7 things that I'm going to be attaching to the dyno out there to get the calibration done. The first thing is the bar that we talked about that I just showed you. And we saw that weighed 7.44 pounds, and its center of gravity was 1.92 feet from the center of the absorber. So we'll multiply 7.44 by 1.92 and get 14.28 foot-pounds. And then, so this column here will be how each component contributes to the total torque. And then, in this column over here is going to be the sum of those as we go down. So basically that number there is that plus that, and that number there is that plus that plus that, and so on. So we got the bar that I showed you. There's a carriage that I made to put the weights on as I apply them, and then I have 5 different weights, and they're just weightlifting disc weights. They're 20 pounds each, but here's the weights that they actually came out to be after I weighed them. And then, so the carriage and all these 5 weights are all 3 feet from the center line of the absorber. And these numbers here are what we want to see on the screen as we apply those weights. So the next thing to do is just get the torque program up and running. It'll zero itself, and then we can start attaching pieces to it. And hopefully, if everything's pretty good, these numbers are what's going to be showing up on the screen. So let's go do that next. Okay, so now this is all zeroed out and the program's running. Now the next thing to do is to take this off of here and start installing that bar. And the other thing is I've got a logger running at the same time, a slow logger running now, so that in case I have camera problems like I had before, we can still review the data. Okay, so now I'm going to apply weight A onto it. Weight B. Weight C. Weight D. And finally, weight E. Okay, so all in all, I'm pretty happy with the way that calibration turned out. And, you know, it looked like in certain spots I was reading just a little low, and towards the end I'm reading a little bit high. All things considered, I'm happy with the way that calibration turned out. I'm going to run it like that. For what I'm doing here, me being off by 1 or 2 foot-pounds, and on average I would say I was probably off by 1 foot-pound altogether. But for me in here, with what I'm doing, I'm not going to worry about that. I'm not going to worry about 1 foot-pound. This is the calibration I'm going to use. This is the way I'm going to run it from now on. And then probably what I'll do is put this on a schedule. Just because it's passing my calibration now doesn't mean it'll pass that calibration a year from now. So this is something I'm gonna do from time to time, maybe once or twice a year. That way I'm keeping an eye on it, making sure that over time I'm still producing the same quality of results as I was before. Well, anyway, I'm pretty happy with the way that turned out, and that's about all I got time for this week, and I guess I'll see you next time.